All right, folks, you're going to get your calculators out for this, and if you have one of the note sheets that you picked up in class, you want to use that now. For video 2.3b, we're going to do some gravitation problems. I'm going to jump right in. First one is just a straight up calculation. So this one is kind of rare on an AP exam, but still could pop up. Calculate the magnitude of the gravitational force between the Earth and the Moon. The data I give you is approximate: the mass of the Earth, the mass of the Moon, and the distance between their centers of mass. So this one is the most straightforward. We can calculate the force of gravity by doing big G times the mass of Earth times the mass of the Moon divided by the distance between their centers squared. 6.67 times 10 to the negative 11th is big G. 5.97 times 10 to the 24th is the mass of the Earth. 7.35 times 10 to the 22nd, mass of the Moon. And then 3.84 times 10 to the 8th, that gets squared for that. Awesome. So this is an exercise of I think you should do this in your calculator because you want to make sure you can handle all of this scientific notation. If you happen to be doing this by hand, you want to remember that when you square a number in scientific notation, you square the coefficient. So square 3.84, and then you multiply the exponents, 8 times 2. There's also rules for exponents up top, so you would add the exponents up here and multiply the coefficients. But if you have a graphing or scientific calculator, it can do all of that for you, and you will get 1.98 times 10 to the 20th newtons. So that one is really just so you can do scientific notation. Next problem starts to get more like what you would see on the AP exam. A box has a weight of 650 newtons on the Earth. What is the weight of the box on a planet with twice the mass of the Earth and 3 times the radius? So the force of gravity is G times m over r squared. The equation uses m1, m2. I prefer capital M, lowercase m, if I can get away with it. And I started to do something like this in class with tension, and I'm going to show you a way to work this. Now, the weight on Earth is due to the mass of the Earth and the radius of the Earth. What I have in the problem is the ratio, essentially, of the mass of the new planet to Earth and the radius of the new planet to Earth. What I'm going to do is what I did in class is do Fg prime. Now, Fg prime would be like the new weight of the box. And I'm going to do it in terms of the old weight of the box. So the new weight of the box, big G, has not changed, but the planet is now double in mass. So m becomes 2m. The mass of the box hasn't changed, so I'm going to leave that as m. And then the radius of this planet is 3 times the radius of Earth. Now notice how r has the square operator on it, and so now 3r has the squared operator on it. So I have to preserve all of the math of this equation when I do it. So my goal is to figure out what the new weight is in terms of the old weight, and I do that by applying the math in the equation. So the question is, if I double the mass and triple the radius, by what factor does the force of gravity change? Well, all of the numerator is multiplication. So I'm going to rearrange the numerator. I'm going to do 2, and then over here I'm going to write G, capital M, lowercase m. I'm actually going to split it into 2 fractions. So I'm going to leave the variables there, and because I know how multiplication works, I'm going to extract that number 2, and I'm going to put it out front. And you'll see why in a minute. I'm going to do the same thing with the denominator, but I have to square everything first. So I get 3 squared times r squared. Well, 3 squared is 9, and then r squared is r squared. So mathematically what I've done is I've taken these factors by which the mass and the radius have changed, and I've taken them out of the equation. I've done all the math I need to do, and now they're out front. And what I want you to notice is that G, big M, little m over r squared is the original weight of this object. So these variables represented a weight of 650 newtons, and I've still got them there. So my new force of gravity, my new weight, is 2/9 times 650 newtons, because that was the original force of gravity. And then I just calculate that. This new force of gravity is 144 newtons. There are other ways to do this, and I might explore that during class, but that's the one that I like the best because it's the quickest for me to do in my head. You can also do this by making up numbers. All right, this last one is a little bit more involved. I'll let you read that one. And I drew a diagram. I'm going to label the masses here. So this moon has a mass of m. The planet has a mass of 40 m. And the sun has a mass of 120 m. The distance between the planet and the moon's center of mass is r. And the distance between the moon and the sun's center of mass is 10r. And so before we do anything, we're looking for the net force on the moon in terms of these variables. The moon is going to get pulled in two directions. It gets pulled to the left by the planet, and it gets pulled to the right by the sun. So I'm going to have to find the net force on this. Before we get our answer, I just want to show you, like, this value of r is significantly smaller than this value of 10r. That means that the planet's gravity has a lot more impact on the moon than the sun does. And so we'll see that play out. So net force. I don't really have an equation for net force. I'm not using Newton's second law. I'm just trying to find the net force. So the net force is going to be the force from the sun, because I'm going to make the right direction positive. The moon's going to get pulled to the right by the sun, so I'm going to make the sun's force positive, and then it's going to get pulled to the left by the planet, so I'm going to make the planet's force of gravity on the moon negative. Right. So now I have to figure out what the force from the sun is. Well, the force of gravity is, in my last equation, g/m/m over r squared. So for the sun, the force of gravity is going to be capital G times 120 m, that's the mass of the sun, times m, that's the mass of the moon, divided by 10r squared, because that is the distance between those two centers. Same thing for the planet now. The planet's force of gravity is big G times 40 m, that's the mass of the planet, times m, that's the mass of the moon, divided by r squared. So that is the math that I have to work with to get the net force. So all I'm doing is I'm actually kind of pretending that all of these things are actual numbers, and I'm putting them into the gravitation equation. But because the moon gets pulled by two objects, I have to have two terms to get my net force. All right, so now we're going to go up here, and I'm not going to write net force anymore. I'm going to now extract these numbers. So for the sun, 120 over 10 squared times g m over r squared minus 40, it's really just 40, times g m over r squared. And so that's really it. I have to figure out, I can actually write it like that and leave it, but I want to work the numbers a little bit more. So I actually have like terms. g/m over r squared is the variable essentially in both terms. So if I just subtract these two numbers, then I can get my answer. So 120 over 100 minus 40 times g, and I'm going to simplify this, m squared over r squared. Well, if you do this out, you get 38.8. So that is negative 38.8 g m squared over r squared. And that's it. So I have worked with the relative masses and distances and found an expression for net force. And so we will go over some more gravity problems in class probably, so you get some more looks, but that's it.